We're going to finish up with the examples, for the class examples for curve sketching number 2. It says sketch the graph of the function and find the below information. We have rational function 2x squared over 9 minus x squared. Now there's quite a bit of information that we can find without going to first or second derivative. We can find the vertical asymptote if there's any, horizontal asymptote, we can find x and y intercept, and also we can determine domain. Now we see some variables in the denominator, so that could lead us to where the graph may have a vertical or horizontal asymptote. So vertical asymptote is where we can set the denominator equal to 0 and solve for x. So if we set denominator equal to 0, we're going to get plus or minus 3. So we have two vertical asymptotes, x equals 3 and x equals negative 3. Horizontal asymptotes, we can determine that. Think of it as finding the limit as x approaches infinity. And here we have degrees that are matching. So we just take the leading coefficient. So 2 over negative 1 is negative 2. So we have horizontal asymptote at y equals negative 2. X-intercept, replace y with 0. We only look at the numerator. So 0 equals 2x squared, so x equals 0. So 0, 0. And y-intercept will always be, also be the same thing. 0 over 9 minus 0 is 0, 0. So we have x-intercept at 0, 0. We have vertical asymptote at x equals 3 and x equals negative 3. And we have horizontal asymptote at y equals negative 2. Okay, so we can now think about the behavior of the slopes and curvature by looking at f prime and f double prime. So f prime, we have to go through quotient rule. So f prime g minus f g prime all over g squared. Now to clean this up, we can distribute the 4x through, combine this to be positive 4x cubed, and we have two terms that cancel out. So we're left with f prime being 36x all over 9 minus x squared, quantity squared. To find critical points, remember critical values can come from both numerator and denominator as long as we have variables there. So from numerator, we'll get a 0. From denominator, we get plus or minus 3. So we put those values onto the sign line, and we choose values in each interval and plug into the derivative because we want to determine, we only care about the signs. Negative sign would mean that the graph has negative slope there. Positive means positive slope. So if I pick negative 4, I'll get a negative. If I pick negative 1, I'll get a negative value. If I pick positive 1, I'll get positive. If I pick positive 4, I'll get a positive. Everything is only based off of numerator. Denominator will always be positive because of the squared. So now we know that there's not going to be any relative extrema even at negative 3 or 3 because we know there's vertical asymptotes there, but we do know that 0, 0 exists, and the change in slope indicates that we have a relative extrema, a relative minimum at 0. Okay. Now to get to the second derivative to determine concavity, we're going to go through, look at first derivative and determine that we have to go through quotient rule again. So f prime g minus f times g prime. When we get down to g prime, we have to go through chain rule. So we bring down the 2, keep the parentheses, subtract 1 from the exponent, and then multiply by the inside function's derivative. 9 goes to 0, negative x squared becomes negative 2x, and now all over denominator squared. Okay. So all this should be to the 4th. Okay. Rather than expanding everything out, we can try and factor what we see between these two expressions. So looking at this expression and this expression, we see that they both share 36 and they share a 9 minus x squared. So if we pull that out, then we can make our factoring simplifying step a lot faster, a lot more efficient. So if we take out 36 minus 9x squared, we see that the only thing that is remaining, if we were to remove 36 9 minus x squared from the first expression, we'll only be left with 1 9 minus x squared. From the second expression, which is this whole term here, if we remove 36 and 9 minus x squared, we'll be left with 2x and 2x, which gives me positive 4x squared. So we combine those inside the bracket and we get 9 plus 3x squared. One of the 9 minus x squared will cancel out with the numerator and denominator. So that leaves us with 36 times 9 plus 3x squared all over 9 minus x squared cubed. So we have our second derivative. Numerator, we see that no critical points here because if we set this equal to 0, we'll get an imaginary number. If we set the denominator equal to 0, we'll get plus positive and negative 3. And now we know there's vertical asymptotes there, so that's why these critical points keep showing up. And now we choose values in each interval. Here I can plug negative 4 in, I'll get a negative. If I plug 0 in, I'll get a positive. If I plug 4 in, I'll get a negative. Now you see that there are change in signs for concavity, but we know that these cannot be points of inflection because these points do not exist on the graph. These are vertical asymptotes. So we see, we know the concavity for the graph, we know the slopes for the graph, so we can put these pieces of information onto the same sign line so that we can match the concavity and the slopes for each portion of the graph. So to the left of negative 3, we want a graph that is decreasing and concave down. So decreasing and concave down, we know that these vertical and horizontal asymptotes are going to give this graph shape. Between negative 3 and 0, decreasing and concave up. So that's this portion, decreasing, concave up. Increasing, concave up. So from 0 to 3, increasing, concave up. And finally, increasing, concave down. Increasing, concave down. We have the horizontal and vertical asymptotes there to give the graph shape. So now based off of this information, we can fill in the rest of these values. We have x and y intercepts. We know x, vertical and horizontal asymptotes. Our domain is all real numbers except for our vertical asymptotes. Interval increasing, we just look at the sign line that we created. Interval decreasing, there's no relative max, but we do have a relative minimum. No points of inflection. The change in concavity occurs where the vertical asymptotes are, so we know there's no points there. And finally, we look at the concavity sign line to determine concave up and concave down.